Hello and welcome to your preview of Training to Go modules presented by Technical Sales and Consulting. This is a preview of our Power Management Training module. At the end, we will provide how to access more information about our training products. Thanks for visiting, and we hope you enjoyed the preview. For more information, visit our website, trainingtogo.net.
Be generated and distributed. Having an understanding of this process is essential to the power management process. Electrical power used in residential, commercial, and industrial buildings is mostly generated by the utility at a central point and transmitted and distributed to where it is required through the utility power transmission and distribution system. The electricity is generated from these sources: coal 33%, natural gas 33%, nuclear 19.5%, almost 8% from non-hydro renewables like wind or solar, 6% from hydro and less than 1% from oil. Let's examine this illustration to get an idea of a transmission and distribution system. T&D for short. A utility power transmission and distribution system controls, protects, transforms, and regulates electrical power so it can be safely delivered to the user. The utility power transmission and distribution system begins at the point of power production and normally ends at a building metered service entrance point, which is where the building distribution system begins. Perhaps stepping through this diagram will be helpful. Later we will zoom in closer to the key areas. The electricity journey starts at the generating station. We previously mentioned the various sources used to generate power. At the station, a step-up transformer is used as seen here. After stepping up, the voltage power is then sent through transmission lines. Now, what is a transmission line? A transmission line is an aerial conductor that carries large amounts of electrical power at high voltages over long distances. You might hear engineers refer to these as high-tension lines. The transmission voltage level is determined by the required transmission distance as well as the amount of power carried. A larger transmission voltage is chosen when dealing with longer distances or larger transmitted power levels. As you can see, these voltages have a wide range. Why such a high level? Well, one of the basic principles of electricity is that the higher the voltage, the lower the current. By lowering the current, greater distances can be maintained with less losses and the size of the current carrying conductors can be reduced, thus providing a great savings. At this point of the journey, there may be a large industrial facility with a high electricity demand, such as a manufacturing plant, chemical processing facility, or a large data center, that purchases power at 138 or 230 kV. As the transmission lines continue to move the power, they can connect to a substation which utilizes a step-down transformer highlighted here to drop the voltage as required by the customer and sent over distribution lines highlighted in green here. These voltages include 26 and 69 kV for the sub-transmission customer, 4 and 13 kV for what is considered a primary customer, and 120 and 240 volts for the secondary customer. From this point, the power is distributed as needed through these facilities. Distribution substations provide a convenient place along the distribution system for maintenance, checkpoints, and power line adjustments. Let's take an in-depth view of a typical distribution substation. One of the best images is provided by the OSHA website. It shows the power flow through the substation and the various pieces of equipment needed. Coming up, we will touch on each piece of equipment. First, you see the incoming sub-transmission lines. In this case, the incoming voltage is 34 kV. In conjunction with the incoming line, you will see lightning arresters. The feed then flows to air brake switches used to isolate for service the equipment in the yard. These can also be vacuum switches and can also be enclosed in the transformer. Next, in this illustration, you will see oil circuit breakers. Oil circuit breakers are old technology but still exist in some older substations. Today, the breakers of choice are vacuum and SF6. There are also some substations with outdoor enclosed air breakers. Next is the step-down transformer. Transforming from 34 kV to a more utilization voltage of 7.2 kV. This usually uses oil for cooling and insulation. This oil in today's transformers is an environmentally friendly, non-toxic fluid called FR3. The secondary of the transformer feeds voltage regulators which in turn are connected to medium voltage metal-clad switchgear. The switchgear contains feeder breakers. The number of breakers depends on the load capacity and the needs for distribution feeds. The load side of these breakers are connected to a bus configuration fused cutout switches on a rack assembly. It is from here that the power is connected to the outgoing distribution line poles. Coming up we examine these components in more detail. You never know when lightning can strike. It is a good idea to take the necessary protection measures before it happens. When designing substations, it is essential to install lightning arresters. Here you see lightning arresters installed on the primary side of a substation transformer. These also can be installed on an overhead rack on the load side of the incoming line disconnect as was pictured on the previous slide. Lightning arresters work to suppress surges and lightning by using MOVs or metal oxide varistors similar to those found in the surge suppressors in your home, except they are much larger and heavier duty to allow for absorption and dissipation. There are three types of lightning arresters, each for application is their own specific voltage range. Distribution class, which as the name indicates are suitable for use in distribution substations. These are rated 2.4 to 46 kV. Intermediate classes are also available and can be used in distribution substations. These are available from 2.4 to 138 kV. The highest rated lightning arrestor is the station class. These are designed to be used at the generating station but can also be used in distribution substations. These are available from 2.4 kV to 230 kV. As you increase in the class selected, the better lightning protection is achieved. As an example, let's assume this distribution substation was an incoming voltage of 34.5 kV. You could opt for station class arresters. Sometimes design engineers opt to place the arresters on the substation transformer. If that is the case, distribution arresters on the 13.8 kV secondary would be selected. It is necessary to isolate the circuit breakers, transformers and other equipment. One option is to use an air brake switch manufactured by Southern States seen here. This is a single pole but can be grouped with two other units for the required 3 poles. These are non-fused and can be operated with a manual crank seen here or with a motor operator seen here. The 3-pole group operated switch and mechanism is seen here. If properly maintained, distribution substation breakers have a very long life. You may encounter some older ones that use an OCBs or oil circuit breaker. This is typical of one. At first glance you can tell that these are vintage and dated, however the design is sound and works well. The tank arrangements and control panel may have different orientations. These are located before the substation transformer and provide the feed to the primary side of the transformer by round bus bar. This diagram shows the configuration. Let's zoom in. The external bushings allow for the conductor to be connected. These penetrate the tank and connect to the fixed and moving contacts. The oil in the breaker tank insulates the current carrying parts and also cools the contacts to prevent overheating. When the breaker is interrupted, the arc energy is absorbed by the oil. In addition, the oil reduces wear and tear and prevents oxidation. Another old-school device would be an air circuit breaker or ACB. When you see them in a substation yard, they look huge, almost the size of a large shed. They need to be that way in order to house the arc chutes used to extinguish the arc during interruption. This photo shows the breaker out of the weatherproof house. The arc chutes are located here. This illustration depicts how the arc is extinguished with an air circuit breaker. The image on the left shows the breaker contact closed. When it is opened or interrupts a fault, the arc is moved by the arcing contacts toward the arc chute. The arc chute consists of stacked plates with a gap in between. The arc is then spread out across the plates until extinguished. Coming up, we will look at 2 other options for substations, including air, vacuum, and SF6 breakers. Disturbances in an electrical system come in different forms. It is important that we have an understanding of these. Here are the ones you are likely to encounter in your journey for power quality. The first is power failure. A power failure, also known as a power interruption, is a complete loss of electricity and is considered the most severe form of poor power quality, causing immediate disruption to all connected devices and systems, leading to potential data loss, operational downtime, and potential damage to sensitive equipment depending on the duration of the outage. All of this translates into massive economic losses. Next is a power sag. A power sag, also called a voltage dip, significantly impacts power quality by causing a temporary drop in voltage, which can lead to malfunctions in sensitive electronic equipment like computers, industrial controls, and motors, potentially resulting in data loss, operational disruptions, and even equipment damage due to the sudden decrease in power supply during the sag event. This can manifest as dimming lights, computer freezes, or unexpected machine shutdowns depending on the severity and duration of the sag. A power surge impacts power quality by causing a sudden, temporary increase in voltage, which as seen with a sag, can lead to damage to electronic devices and appliances by overheating their internal components, potentially resulting in malfunctions, data loss, reduced lifespan, or even complete failure depending on the severity of the surge. Even small surges can gradually degrade sensitive electronics over time. Now undervoltage is when the voltage from a power source drops down below the nominal level for a sustained duration. This is sometimes referred to as a brown-out or brownout condition. It results in similar reactions as seen with a power sag on equipment. Undervoltage can also cause damage due to increased current draw when devices try to operate at a lower voltage level. Essentially, it can disrupt normal device operation and shorten their lifespan. Next, overvoltage refers to a situation where the voltage in a power system exceeds its normal level, which can negatively impact the quality of power by potentially damaging electrical equipment if sustained for a significant period, leading to overheating and potential failure due to excessive voltage stress on components. Harmonic distortion is the presence of unwanted frequency components in a power system. These unwanted components are integer multiples of the fundamental frequency, usually 50 or 60 Hz, and can significantly impact the performance and reliability of the power system. These multiples or fundamentals are displayed in the wave form. For example, this image shows a multiple of third harmonics. To better understand and provide data to help eliminate this, a calculation is available to ascertain the total harmonic distortion or THD. Another nuisance that causes issues for electronic equipment and disrupts data transmission is line noise. This refers to unwanted electrical disturbances on the power line, which significantly degrades power quality by introducing random variations in voltage and waveform. Essentially, it acts like static on a radio signal, corrupting the clean power supply needed for proper functionality. This causes havoc on communication lines in a facility such as Wi-Fi. Switching transients significantly impact power quality by causing sudden, high-frequency voltage spikes or dips when electrical circuits are switched on or off, potentially leading to insulation breakdown and equipment damage due to the rapid change in voltage and current levels within the system. Frequency variation in a power system significantly impacts power quality by causing issues like motor speed fluctuations, potential equipment damage, reduced efficiency, and even system instability, primarily affecting devices that rely on a consistent power cycle, like motors and sensitive electronics. As the frequency deviates from the nominal value, a lower frequency results in slower motor speeds, while a higher frequency can lead to overheating and potential damage. We will revisit these terms later in this lesson as we introduce remedies to prevent or eliminate these disturbances. Eaton, Schneider Electric, Square D, Rockwell Automation, Allen Bradley, and General Electric are prominent manufacturers offering power management solutions. Here's an overview of their offerings. First, let's look at Eaton. Their power management software is called Power Expert. It features real-time monitoring, data analysis, and system diagnostics. Group Schneider's tool is called EcoStruxure Power Monitoring Expert. It mainly covers energy usage analysis, power quality monitoring, and predictive maintenance. Rockwell Automation or Allen Bradley's product is labeled FactoryTalk Energy Metrics, featuring energy consumption tracking, reporting, and integration with control systems. Lastly, GE or General Electric's line is PQM2 power quality metering. Their main feature provides continuous three-phase system monitoring, power factor correction, and programmable setpoints. Now let's highlight some differences. Eaton has strong integration with Eaton hardware, advanced analytics, and cybersecurity features. Group Schneider provides extensive IoT connectivity, which stands for Internet of Things, which encompasses various technologies and protocols that enable a wide range of devices to connect to the Internet and each other, facilitating data exchange and automation across diverse applications. They also are very good at cloud integration and AI-based insights. Allen Bradley offers seamless integration with Rockwell Allen Bradley automation systems for industrial applications. GE is more focused on hardware-based metering rather than advanced software-driven analytics. Here are some key takeaways. Eaton Power Expert is best for cybersecurity and data analytics in power monitoring. Schneider EcoStruxure excels in IoT connectivity, provide more ways to connect and predictive maintenance. Allen Bradley FactoryTalk is ideal for industrial automation and control system integration, and GE PQM2 is hardware-focused, offering robust power quality monitoring.
Hi, we hope you enjoyed the sample video of our online e-learning module. This clip is from one of our many available modules. We are always working on new modules, just like this power management course. Here is the current list of developed lessons. Did you know that 16 of our courses carry 22 NETA CTD credits? And we have courses suitable for Pennsylvania and Delaware CEU credit. New modules are being constantly added, so check back with us on our website trainingtogo.net. Let our Training to Go programs train your people while you run your business.